So here I'm going to show you some of the important details about solving linear systems in MATLAB. The details do depend on MATLAB in some ways, but if you were using another environment like Python or Fortran or C with particular numerical libraries, the process would look a lot the same. You'd just be doing it with different function calls and that sort of thing. So here's our favorite 4x4 linear system that we've been doing over and over again. And again, just to review, to solve a single linear system, AX is equal to B. Well, in mathematical terms, we would write X is equal to A inverse B. But in MATLAB, A inverse B is done as A backslash B. Well, now we know what that does. What that does is pivoted LU factorization, followed by two triangular solves to find X. Now, when you get X, you don't usually know what the exact solution of the system is, so it's a little hard to say what the error is, but we can always check what's called the residual. So if X is supposed to solve AX equals B, well, we can take the difference between B and A times X, and we should get 0 ideally, or at least get something small. Here it's small compared to machine precision. All right, now sometimes it happens that we want to solve multiple linear systems, all with the same matrix A, but with different right-hand side vectors. And to do that, we use a linear algebra trick. So if we're trying to solve AX1 equals B1, AX2 is equal to B2, and so on. So each B is different, and so each X is going to be different. Well, what we can do is we can define a matrix X whose columns are the solutions that we're looking for. And then we know from our rules of block multiplication that A times capital X is just A times X1 followed by A times X2 and so on out to the end. And we know that each one of these is supposed to equal one of the B's. So we can call this matrix on the right just capital B. So now we want to solve A capital X equals capital B. B has k columns. Here we have 6 columns for 6 different right-hand sides. And again, capital X is equal to A inverse times capital B, which is the same thing as A backslash B. It does LU factorization followed by triangular solves for each column of B. And in this case, when we compute the residual, it'll have 6 columns, all of which we hope are small. Okay, now there's another situation where we want to solve multiple linear systems, but we don't know all the different right-hand vectors at once. And so I call these the case of sequential right-hand sides. So for example, here's a loop that actually does something important. We'll find out about it much later in the course. Don't worry for now about what it's trying to accomplish. Just look at what it does. So we start with a vector v. Okay, we loop 10 times. So first we apply A inverse to v, or if you like, we could think of this as solving AW equals v. Given v, solve for w. And then we compute a new version of v based on the answer that we got for w. Okay? Then we reach the end of the loop and we start over again. Well, now we have to solve a new linear system, A backslash v. I didn't know this v now at the beginning of the loop. So now that k is equal to 2, I know what v is. I won't know what v is for the next iteration of the loop until I finish doing this line again, and so on. So it's not as though I can set up all the right-hand sides into one big matrix at the start. I have to do them one after the other. Well, if you think about it, though, this is kind of wasteful, right? So it's the same matrix A every time through the loop, So we do this pivoted LU factorization each time through the loop. That's 2/3 n cubed flops each time. But A doesn't change, and so its PLU factors don't change. And so I'm just redoing the same work over and over again. So instead, the smarter thing to do is to take that computation outside of the loop. Do it before. So before you start looping, you pre-compute the factorization. So once we have the L and the U factors, right, then these are the two steps. We first do a forward substitution, we do a backward substitution to find W, and then we find the new V at the end of the loop and go back to the beginning again. So now we're solving multiple right-hand sides, but we're only doing the LU factorization once. And we can show that these forward and backward substitution steps actually take on the order of n squared flops. So, of course, here n is extremely small, we don't care. But if n were big, there's a big difference between 2/3 n cubed and n squared flops. Now, one last thing is you might be wondering in this loop, why did I just call LU? Why not LUP? What happened to my row pivoting? So the answer to this is kind of complicated, but remember that we had PA is equal to LU. Well, that means we can write that A is equal to P inverse L times U. And we can group these two together. So in MATLAB, when you ask for just the L and the U in an LU factorization, the L is actually this whole matrix here. So when we execute this statement, see the U is upper triangular, but the L is not actually lower triangular. Instead we would say that this is permuted lower triangular. In fact, the inverse of a permutation matrix P is also another permutation matrix. And so we're just permuting the rows of L in a particular way. Well, you also might be curious about the fact that we use backslash in different ways. So going out to the beginning, when we say A backslash B, it's a general matrix A. MATLAB does the LU factorization, or the PLU factorization, and then does two triangular solves all at once. But when it comes to something like this last loop, when we have an L backslash or a U backslash, well, with U backslash, MATLAB detects that U is upper triangular, and so it immediately jumps to back substitution. And when you give L backslash, MATLAB's able to recognize that it has this special permuted lower triangular structure. And so it's able to do that solution with a fast triangular solve as well. So those two steps in this loop really are n squared. It really does skip the factorization step when you give a triangular matrix.